Greetings, BCal students. Today we're going to be going over the basic properties of the derivative. You can find this information in chapter 4.1 in the ebook. We're going to start off by discussing some notations for the derivative. We're already seeing this one where we realize that f prime of x, and just as a reminder, that the derivative f prime of x is defined as the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Okay, so very important. Always keep that in mind. This will always be the root that we come back to. Whenever someone says, what is a derivative? This is how a derivative is defined right here, right? And remember, this is change in y over change in x when you have a very small change in x. Okay, so that's where we are here. So we can also write this as y prime. Very common to write this as y prime. Also, dy dx is a very common way to write it. Think about this. You know, when we're looking at the derivative, y prime. Well, that's one way of thinking about this is we're taking the limit as delta x approaches 0 of delta y over delta x, right? And so this is capturing this this notion right there. All right, df dx, kind of the same thing that's going on here. Writing it like this is also very common. You write d over dx, and then you put a brackets there, and then whatever you're taking the derivative of goes inside. Less common, we won't be using this nomenclature as often as these other guys. These guys we'll use pretty clearly. These last two, not quite so often. This d right here, this just means derivative, and then you take the of f of x. That's all that means. And this one's even more specific. Again, derivative of the function, but note the difference is we've got this little x right there that's telling you what the variable that you're taking the derivative of, because sometimes there could be other letters in the expression that stand for constants, and so this just makes it more specific. All right, so keep all these in mind when working through. They all mean exactly the same thing. Okay, so now higher derivatives. So we have second and third order derivatives we're going to talk about. Of course, there are higher orders than even that, but let's just focus on these for now. Second derivative is simply the rate of change of the rate of change, right? The first derivative is a rate of change, so if you take a derivative of that, then you have the rate of change of the rate of change. And you can kind of capture this notion over here. We've got 2 primes, derivative of the derivative, same as y double prime. And so look at this right here. This is the rate of change. And then, note the brackets here. It's the same as this notation here. We are taking the rate of change here of the rate of change. Very common to write it like this. This is read as the second derivative of y with respect to x. So once again, that is the second derivative of y with respect to x. And you can really capture everything going on right here. Note it's the same derivative formula we've been dealing with before, with one crucial difference. We're taking the derivative of the derivative. Okay. So some quick physical examples, because we can all kind of relate to the basic level of physics, even if we're not gifted physics students. We all have some everyday experience with velocity and acceleration and getting jerked around in our car, hopefully not too erratically. The velocity is the rate of change of the position function, right? And where s of t is the position function. You're saying what is your position at time t. And so v of t, that's the velocity at time t, is simply defined as s prime of t. And then note we've got our Leibniz notation here, ds, the change, the derivative of the position with respect to time is how you would read that. All right, so what is acceleration? We've all been in a car that was accelerating at a constant rate. Acceleration is the rate of change of the velocity function. AT is equals the derivative of the velocity, which is dv dt. But what is going on? We're taking the rate of change of the rate of change. It is the second derivative of the position function. And this guy right here is read as the second derivative of the position function with respect to time. And we can also write, of course, as s double prime of t. All right, so what happens if the acceleration isn't constant? What happens when you're traveling along and all of a sudden your acceleration changes drastically? An example of this could be when you're sitting at the stoplight, your acceleration is 0 because you're standing still, and all of a sudden you mash on the accelerator. Well, now all of a sudden you're being jerked back into your seat, and that is the jerk equation, right? It is the rate of change of the acceleration. And so typically it's used as j of t. The jerk equation is the a prime of t, which is again the derivative of the acceleration function with respect to time. And over here we have the derivative of the velocity function with respect to time, second derivative of the velocity with respect to time, v double prime of t, or s triple prime of t. Now, of course, you could take the acceleration of the jerk equation and keep on going and going. What is the physical meaning of the derivative of the jerk equation? I don't know. It's not something that we as human beings can really have a feel for, if that's at that rate of change. But what we do have a good feel for is velocity, acceleration, and then when we're getting jerked around. Okay, so higher derivatives. It may not surprise you that there are derivatives higher than this. For instance, the fourth order derivative. We've got a little 4 right here. Now, why would we put parentheses and then a 4? Well, when you get to 3, that's pretty easy to see. But when you get to the fourth order derivative, it starts getting a little crowded. But what if it's a fifth order derivative, or a 6th, or a 7th, or an 8th, or a 9th, or a 10th? You can imagine it gets really unruly after a certain point. So the typical standard is we use up to 3 tick marks, and after the third tick mark, then we start using this right here. All right, so this is a fourth order derivative, the fourth derivative of y with respect to x. And now what is the fourth order derivative? But it's the derivative of the third derivative. Okay. And to put this in more general terms, higher in-order derivatives, where n is just some positive number greater than 0. This would be the nth derivative. Note it's still inside those parentheses. And so here we would say the nth derivative of y with respect to x. And what is the nth derivative? But is the derivative of the n minus 1th derivative. Okay, so let's do a quick example here. I know I have the whole page set up. You're not going to need anywhere near this whole page, but if you need some extra space to write on, you've got it here. So the second derivative of y is 2x. Well, what is the third derivative? Well, the third derivative is simply the derivative with respect to x of 2x. And we know this is going to be 2 already. I believe this is one that we did in a previous handout, so let's go ahead and write that. it's going to equal 2. If you have trouble seeing that, also think it's, it's the slope of the tangent line. Well, any line tangent to 2x is going to have a slope of 2. All right, so that's the third derivative. But what about the fourth derivative? Well, that's simply going to be the derivative of the third derivative, which is simply the derivative of 2 with respect to x, which is 0. Okay. And then, of course, the fifth derivative would be 0 as well, so with the 6, any derivatives after that would all be 0. All right, so again, when you go to higher order derivatives, it's always just the derivative of the lower order right before it. All right, so let's take a look at this part here. We're gonna start proving some more properties of the derivative. Note that everything that we're going to see here are all special cases of this guy right here. All right, so let's go ahead and fill this out. We already looked at this earlier on. The derivative of a constant is always going to be 0. All right, just think of the graph of the constant function. There's our x and y graph. Constant function always looks like that. What's the slope of this line right here? Well, it's always going to be 0. So you can clearly see why that would be 0 right there. All right, now what about 2? We've already looked at this one as well. It's 1, right? Because this is just the line y equals x, and that always has a slope of 1. As a matter of fact, we even went a step further. Mx plus b, it's always going to be the slope. All right, so let's take a look at this guy right here. So in order to do this one, you're going to have to utilize something called Pascal's triangle. Pascal's triangle is used to expand terms like this. So let's go ahead and take a look at Pascal's triangle. It turns out it's a good thing that we have all this extra space in the page up here, so we'll go ahead and use it. So Pascal's triangle goes like this. You start off with a 1 at the top. That's your 0 level. And then you go one step down. And you just put a 1 on the outside like that. And then that's your first level. Second level. And so here's where things start getting interesting. We're going to add these two guys together. And so we have 1, 2, 1. Actually, let me use a different color. And so again, this would be n equals 0, n equals 1, n equals 2. And now let's go on to n equals 3. And so again, we just put 1s on the outside, and then everything above kind of trickles down like this. And so we've got 1 plus 2 and 1 plus 2. All right, so we go on to the next one. And now we're at n equals 4. Again, just put another 1 on the outside. Everything above goes down. And so we've got 1 plus 3, 3 plus 3, 3 plus 1. All right, let's just go one more down before we start generalizing this. N equals 5. And so again, 1's on the outside. Everything above feeds down like this. 1 and 4, 4 and 6, 6 and 4, and then 4 and 1. All right. So before going any further, I want us to note the pattern here. We'll start it on this guy here. N equals 2. Note how we have a 2 right here. N equals 3. Note how we have a 3 right here. n equals 4. There's a 4 right here. N equals 5. And then we have a 5 right here. And note that part of the reason why these match is that, every time we go down a step, we increase by 1. And what's going on with this number here? Well, we've got a 1 plus the number before it. So it's tracking it as we go down. So when we get down to, say, n equals some, big N, after, quite a few iterations, what's going to happen? Well, we're going to be left with, again, 1 will always be on the outside. The next number will match. It's going to be a big N. And this, we'll have a series of numbers after that. We'll call it C2, C3. These are just constants. We're just using C2 and C3 just to fill in. And so, it keeps on going on until you finally get to N and then 1 again, right? That's just following the pattern. And this is Pascal's triangle. Now, Pascal's triangle is very useful. It's more so than what you might think. It's kind of an interesting pattern, but how do we use it? Well, let's take a look. So let's say we've got x plus some, well, we'll say h, since that's what we're going to be interested in anyways, to the 0th power. Note 0. It correlates with this guy here. We got 0 there. Well, what is that? What is anything to the 0th power? Well, it's just going to be 1. What about x plus h to the 1st power? Again, we've got, 1, and we've got that 1 matching there. Well, as we all know, that's going to be x plus h, right? Because it's just the 1st power. Now let's look at x plus h squared. That's x plus h times x plus h. When you work it out, you get x squared plus 2 times xh plus h squared, right? So note what the coefficients in front of each one. Right, they match. And so if we were to work out x plus h cubed, and I do encourage you to work this out to verify that this is true. We start off with x cubed, and then the x goes down a power to make it x squared multiplied by h plus x times h squared. Notice the h is increasing, and then plus h cubed. And now we're going to go ahead. I'm going to go and write this in a different colors so it kind of stands out. The one power goes here, 3 here, 3 here, and 1 here. We don't have to write the ones. I just wanted you to kind of emphasize the point. If you work x plus h cubed, that which is just x plus h squared times x plus h, you will get this right here. Note that these coefficients match what you have right there. And that's the power of the Pascal's triangle. If we go to the 4th power, well then it's the same thing. We start off with x to the 4th plus x decreases in power, h increases, and then we've got, just kind of keeps on going down the line. Okay, plus x times h cubed, and then finally plus h to the 4th. 1 goes here, then we've got a 4, a 6, a 4, and then finally another 1. All right, now what about x plus h to the 5th power? Again, same thing. We've got an x to the 5th plus x to the 4th times h plus x cubed h squared. And we just kind of keep on going down the line here until we get to h to the 5th. Give myself a little more room to work with there, and then we put in the coefficients. Five, 10, 10, 5. Good. All right. All right, and so there we are. There we have it. Now, what about the general case, this last one, where we just have some arbitrary n? Well, in that case, this is x plus h to the nth power. Well, so following the pattern, the lead term is going to be x raised to the n plus, the n is going to match there, plus x raised to the n minus 1, because we're going down in a power, times h, plus c2 times x to the n minus 2 times h squared. And then you kind of keep going on, plus c3, x to the n minus 3 times h cubed. And you keep on going down to get to the last term, which is going to be h to the nth power. All right. This is what we were after. This is a nice general expression for when we have an exponent on a binomial, and that's what we're going to need to determine this guy right here. And if you don't see why, you're about to. All right, I'll come back up to that, but first let's get this guy set up. We want to know what is the derivative with respect to x of x raised to the n. Well, that's going to be the limit as h goes to 0 of x plus h raised to the n minus x to the n all over h. All right, that's it. That's our definition of the derivative. We're just simply applying it. Now, what we want to do is we want to expand this term right here. But how do we expand that term? We simply apply this right here, right? It's going to be this whole thing that we're going to go ahead and write in. So let's go ahead and fill that in our handout. X to the n plus n times x to the n minus 1 times h plus c2 x to the n minus 2 h squared, and you keep going on until you get to h to the n. That is our term in yellow. And where the dot 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 is just all the terms in between. And don't forget we have our minus x to the n hanging out all over h. Let's note this x to the n is the same as this one right here. Alright, so first thing we see, we have a positive x to the n and we have a negative x to the n. They're gone. Note that all these terms have an h in them. And we are dividing everything by h. So we're going to get rid of this h, because note if you just plug in h equals 0, where you're going to end up with a 0 divided by 0 error. So we got to massage this work just a little bit. So here we have the limit as h goes to 0, and I'm just going to take out an h term of each and every one of these guys on account of this guy. And so we have n times x to the n minus n plus c2 times x to the n minus 2 times h plus dot 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 h to the n. Right, we're all of the terms in here also have an h term. Okay, so we're going to apply the limit now. Note this first term. There is no h, so we don't have to worry about it. But look at this guy here. This c2 is just a constant. It's just a number. So any number times something approaching 0 is going to be infinitesimally small, right? It's approaching 0. So this is going to go away to 0. All the terms in here will be going to 0. And this term will also be going towards 0. So when we apply the limit, what are we left with? We're left with n times x to the n minus 1. This is known as the power rule for derivatives. That we've only proved it for whenever the exponent is a natural number. Natural number are the numbers 1, 2, 3, 4, 5, 6, not including 0 or any of the negative numbers. It turns out this applies for any number, and we will prove that later on in the course. But just know that anytime you have this setup, the derivative will be this guy right here, and that is known as the power rule. All right, so that's the big one for today. The next one is going to be this guy right here. We're going to show that the constant is just simply multiplied by the derivative. We're going to be able to pull the constant out. So let's go ahead and show this. We want to know what is the derivative of this guy here. So the derivative of a constant times f of x with respect to x simply equals the limit as h approaches 0 of c times f of x plus h minus c times f of x all over h. Okay? All we're doing is applying the formal definition of the derivative. So note we've got the c here and here, so we can pull it out. And note that this c, it doesn't care what h is doing, so we can pull this guy even out of the limit, so that we're left with c times the limit as h approaches 0 of f of x plus h minus f of x all over h. And it's always important to note that this is an operator, right? You never want to write this all by itself, right? It's an operator just like a plus sign is an operator or a minus sign is an operator. It's telling us, this is telling us what to do with this guy right here. If you just write limit h equals, like say, that would be a meaningless statement. You might as well write y equals a plus sign. It makes no sense. So always make sure you've got something after this if you're using it. Alright, so what about this right here? What is this? Well, that's just the formal definition of the derivative. And so we can write that as a constant times the derivative of f. So the takeaway of this is that if you have a constant times a function and you're taking the derivative, just pull the constant right out of the whole thing. And so for 4 we write, what does this equal? This equals the constant times the derivative of the function. You don't have to take the derivative of the constant itself. All right? So that's all I have for today. Have a good day, class.